Welcome to the Midweek Keynote. I'm Ryo Yokota. I'll be chairing this session. Today we have our Midweek Keynote speaker, Professor Bjorn Stevens. Bjorn Stevens is a managing director of the Max Planck Institute for Meteorology, where he leads a department, climate physics. He is also a professor at University of Hamburg. His interests in how atmospheric water vapor and clouds shape climate globally and regionally, understanding how turbulent mixing and cloud microphysical processes influence cloud amount are instrumental in quantifying how clouds respond to warming and how radiative forcing responds to aerosol perturbations. His research has identified different ways in which clouds organize themselves, how varied processes such as precipitation, air-sea interaction, and radiative cooling influence this organization, and how clouds couple to larger scale circulation systems to help determine the pattern of climate change. These interests have led him to advance observational techniques and to expand the frontiers of simulation science to develop and test theories developed by himself and others. So without further ado, please, Professor Bjorn Stevens.
It's good to be here. We're in Hamburg. I'm going to start with a beer. And I'm doing that. This is a Hamburger beer. If you look at it, it's just got a wonderful color, doesn't it? So a lot of you didn't realize this. Well, I'm not doing an advertisement, but cheers. Hamburg actually is important because it introduced, I had that beer because it introduced hopped beer to the world. Most of you probably don't know that, but I'm going to use that analogy of hops and barrels and rules for helping you understand how we can better distribute climate information and the role we all play in that. Beginning in the 13th century, the beer was known as Hamburg export beer. And up until that time, a lot of people were drinking what they call Greit, which is just a sort of a brewed, fermented grain, malted grain. And they would put in sort of weeds and other things in there to give it aroma and flavor. And the British drank Greit until the 15th or 16th century. Hamburg wasn't the very first to put hops in beer, but they were the first to do that in a wholesale way. And it led to a flourishing export economy. Already in 1266, it turns out that Hamburg export beer was the basis for the first Hansa, the trade agreement with London. And that allowed Hamburg to prosper within the Hanseatic League, and it really developed Hamburg's sort of sense of being and who it is. But hops wasn't the only ingredient to make Hamburg successful. In addition to hops, it needed other things. You needed a way to get the beer into people's hands, and there the barrel was really important. So part of the Hanseatic League was trading herring, and you had the herring barrels, and you see that there. The middle picture is one of the oldest pictures known of someone brewing beer, and you know they're brewing because they have what's called the brewer's star up there, the hexagram, the two inverted triangles above the brew and the barrel in the foreground. So you needed to be able to transport. That was another special ingredient. And the third special ingredient was the set of rules, which would sort of valorize best practices, which should set standards for units of exchange. And all of this came together into the Hanseatic League, and Hamburg prospered through that, became a free and imperial city in the Holy Roman Empire, and then today is still called the Freie and Hansestadt, Hamburg. If you look at where that brought us, you see in the city seal, this should change here, but it's not. Try again. Still not changing. It's the beer. So the Hamburg special character is seen here in the seal. The first seal was from the 1200s again. And if you think about it for a second, when you think of city seals, what do you normally see? You see eagles and bears and lions and swords and shields. And Hamburg City Shield, they have the city gate, which reflects this sort of mercantile character, this outward-looking character. Sometimes the gate's open, sometimes it's closed, but it's a place where you go to trade. In the early pictures, you see some religious symbolism, the stars, which were curiously six-sided, and you see the cross. But along the way, this is what the shield looks like today. It looks pretty much the same, again, reflecting this mercantile trading nature of Hamburg. But if you look closely, you see something different. You see the stars above the towers. They aren't the religious six-sided stars, but they're the brewer's cross there above the city. So deep in Hamburg's culture is this freewheeling, outgoing look onto the world, and that's really carried all the way through to the present day. About 150 years ago, as the transatlantic trade really was getting into full steam in Hamburg, they realized that they were taking their wares not just around the well-known coasts of the North Sea, but crisscrossing the Atlantic with major shipping, going to climates that people hadn't been to before. And so if you're driving ships across oceans, going to places people hadn't experienced before, climate information suddenly became valuable. And I think this is the first time really where people understood why information about climate is important, is because people needed that information to transport goods, they needed that information to store goods, to trade goods. And so in Hamburg here, not very far from where we're sitting today, they formed this thing called the Deutsche Seewarte, or the Hamburg Naval, well, it's a German naval observatory near Landungsbrücke. And there they had a department which was led by a guy named Vladimir Köppen, and Köppen was in charge of marine meteorology. And so what they did in the Seewarte, it was sort of a deal. The public sector would collect climate information. All the ships that came into the harbor, they would get the ship's records, they would write down the winds, the measurements, they would outfit the ships with instruments, they would teach people how to use the instruments, and they put together this sailing handbook here of the Atlantic Ocean. And if you look in that handbook, it says 1910, but this came out, the first edition in 1882, and then later in 1885. 600 pages. Half of them are about instrumentation, how to collect measurements, and the other half is exploring the climate of the Atlantic. So 300 pages about the climatology of the Atlantic, and in those 300 pages, a half of those are about storms. So what kind of storms sailors could experience. And you see two images which I took out. One, I don't know if you can see that here. You can see it here. This would be Florida down here, and these are tracks of tropical cyclones or hurricanes over the Atlantic. There's Barbados here. And here's a schematic of a squall, so sailors would know how to work their way through a squall, what would be the events of a squall. So again, it's an example of how climate information was important at that time. But as we spread around the world, we said, okay, we kind of know what it's like. We know there's hurricanes. We know, it's humid in Florida. We know what happens when you go up a mountain. So we collected all this information about the world. We had a pretty good idea of the climates. The guy who put together this book, actually, Köppen, he's also the guy who did the climate diagrams that all of you guys did in school, right? Where you would color in the world and it would say this climate zone and that climate zone. That was due to this guy, Köppen, here. And so we'd have a pretty good idea of what our climate system looked like. So you could say, okay, the value of climate information is now discounted. We all kind of know what it's like. But if you think about it, what we're doing now is we're not taking our ships to distant shores, but we're translating in time and our climate's changing. And so suddenly, again, climate information is becoming valuable. And we're trading climate information more or less in the same way. Here we wrote books and, public entities gathered information, collected it, wrote it down in maps and books and gave it to policymakers, or in that case, shipping industries. Nowadays, we give it to policymakers in the form of books like this, the IPCC, and we say, okay, this is how climate's changing. The whole industry of climate information looks a bit like that. There's just a world of information that you gather and grab and collect. You involve experts, they sit together, they write reports, and they deliver it to the people who commission the reports, and then the people who get the reports commissioned for them pretend that they might do something with that. This might have been okay back in the Köppen day, in the day when you just had to give it to a few ship's captains who were guiding their ships, or a few people who were, shipping beer around the world. But if you think about it today, this doesn't really scale. It's really a boutique way of collecting information. It's very labor intensive. It's hard to extract, and basically it just ends up in some institutional library. And the problem is that it needs to scale. So it seems like every week we're faced with another calamity. So these are from the last couple of years. This is a tornado. These are all real. It's wreaking havoc with infrastructure in Greenfield, Iowa. I used to live in Iowa, so I like that one. It looks like the weather's really mad at the wind turbines there. You'll watch that for a while. On the right is from earlier this year, the Palisades fires, which many of us probably know people who were impacted by those, or the ones in La Cañada. We probably don't know the people on the bottom left. Last week only, there was major flooding in Nigeria that just eradicated a whole village. 150 people disappeared. This one here, some of you might know, that's the Blatten Glacier, which is just blasting down. As the permafrost receded from the mountains, the rock crumbles, it falls on the glacier gave way, all of it came down in a giant deluge on this town. The interesting thing about the bottom two examples are, you could say, is this climate change? Does it really even matter? The point was people weren't really prepared for it. The people in Blatten had 10-day notice. But that town, from what I'm told, in the Swiss Valley, it was like the only place in that valley where it was actually safe to build a town. So if you look in the Swiss valleys, people have tended to put their communities where you wouldn't have rockfalls, where you wouldn't have avalanches. So places where, over time, they realized in the old climate it was okay. But in today's climate, all bets are off. So places that were safe aren't safe. So you're seeing, as we're moving forward in time, there's a need for climate information, and it touches not just on a few ship captains, taking their dinghies and selling beer, but it touches all of us, every sector. So, that's a funny picture of town planning, but that's Blatten after the deluge on the left there. But you see it last summer, the monkeys who had adapted to the climates of north-central Mexico last summer were falling out of the tree due to the heat. So monkeys who had evolved and adapted over eons, suddenly things didn't work anymore. People who set up renewable energy infrastructure are surprised by the amount of dust loading, which wipes out their margins. In Central Europe, actually the Hansa, where they were trading the beer and the barrels on these small ships, a lot of that was through inland waterways. And so the inland waterways, we have many, many centuries of experience of using inland waterways. And suddenly, what do we do when something like the Rhine, that's the Cologne Cathedral in the back, dries up? Mexico City, you see the effect of land subsidence from people tapping the aquifers. Or I do a lot of work in Barbados, and what you see is this invasion of seagrass that is consuming many of the islands, just enormous seas of seagrass. The seagrass washes upshore, and it rots, So people go there with their kids, and they're all proud they're going to this exotic beach for vacation, and there's just rotting seagrass. So that doesn't really do very much for the tourist industry in these places. So climate information has become important for much more than just sailors. There's for many, many sectors, health, food, and on and on. And so the question is really, how do we, the Hamburgians were pretty good at embedding beer in every British person's decision. So how do we embed climate information into decision-making around the world? That's the question that we're trying to ask. And the point I want to make is that it needs a few special ingredients. Jensen likes to call these superpowers. Other people use that phrase too. I'll call them ingredients. And one ingredient is that you need information at scale that represents our best understanding of how things work. And it needs to be at scale because people act at scale. It really doesn't do most people any good to know that the temperature is 1.5 degrees warmer globally. What they want to know is their mountain melting, and will the rocks fall? Is their town in an area that will be hit by changing patterns of storms and might flood and be washed away? So they need information at the scale at which they make decisions. And it needs to represent our best understanding of the physics of how things work, because that's our only way of looking into the future. That's our hops. That's what gives the information its quality, is its scale and the physics. people need a way to access the information. It's one thing to have the information, but if it's bundled in a book, you can't use it. So how do I get you that information? That would be the barrels. And we need, and sometimes we forget this, if you look at how much trade depends on stable rules of exchange. So we need stable rules of exchange to help valorize people's efforts to do things in the right way. And without these superpowers, most of us who make decisions about a changing climate are kind of left with this bad British beer. Great, the stuff with the weeds in it. So let's go through those ingredients, and I'll show you where we're at. We need those three things. We need the hops, we need the barrels, and we need the rules. This picture you might know. You've seen it before, right? So it's the blue marble. It was taken by the astronauts on Apollo 17, I think it was, December 7th, 1972, 52 years ago or so. And if there was ever a single picture which changed how people think about the world, it's this one. So when people saw the world like that, they just imagine before that, nobody really knew what the world looked like. Try to put yourself in the time, when I was born, before that, people didn't really know what the world looked like as a whole. And suddenly you can see it as a whole, and you see yourself in the world very differently. So it's a really iconic picture. And 2 years ago, we decided that we should try to take our model to physics and see if we could simulate that picture. And we did. So we took the very sparse information at the time, particularly in the southern hemisphere, and we initialized our model with that data, ran it forward for 2 days to this day, December 7th, 1972. And that's what we came up with right there. So you see a little bit the power of physics. It can give you a representation of the world which looks very much like what we actually saw from a camera. And when you know that you can do that with physics, the power of physics to generalize, you can do other things. Like if you believe that right picture, it's not perfect, you can see differences, but if you look at that right picture and you say it's a reasonably faithful representation of the left picture, you can see something today that nobody's ever seen before. I have, and the guy who visualized this from NVIDIA, Nicholas Ruber, have seen it, but other than us two, no one's seen it before. And that's what was on the other side of the world on that day. And that's shown here. Okay, it's in moonlight, so you can't see a whole lot because the moon's illuminating it. But those are the storms of the other side of the Earth on the Apollo picture, if you believe the simulation on the right side. And why not? It looked like the actual picture. I don't know if you can see it, but on the very upper edge, you see the lights of the northwest coast of the United States, and kind of near that sweeping cyclone, that's Hawaii, so you just have some orientation. I can make it a bit brighter for you, and you can kind of see, but now you lose the lights of the city. But physics allows you to see things that you couldn't see before. Here, it's not the future, but it's the other side of a very iconic photograph. The physics also allow you to look beyond the simulation of that photograph and, again, connect the front and the back by turning around the planet. We can look at how things evolve in time to see how they work. We can look to here we're looking around the corner towards the South American side and looking at the evolving weather situation. We can go to the Australian side and look over there. We can dive in, we can look at, this is a coupled simulation, look at the height of the ocean on kilometer scales, this ocean surface heights. Salinity of the ocean, you see the freshening up in the Guinean area. The temperature of the ocean, you see the blue upwelling around the Namibian coast. You can see the wind speeds and the very large-scale structure of fine-scale features from the fronts, how they interact with clouds. So physics, we have the physics. We know how to do all of this. The only thing that's been hindering us, this is the hops I'm talking about, the ingredients to provide information at scale, this is at 1 kilometer, has been computing. And computing's got to the point where it's bigger than our planet, so to speak, in the sense that we have enough computer. Oh, something funny happened here. Well, let's see if that goes back. We have enough computer to simulate the planet as a whole on a scale that matters for people. This went black here. Yeah, I like the future. We've done something else just recently, and this is more remarkable. So these simulations were done 2 years ago. They were done at 1 kilometer. And for a very long time, people said, you can't simulate the Earth at a kilometer. You can't do it at this high scale. It's going to take decades. We need other techniques. We did it. Then they said, well, you can't simulate the Earth system. The Earth system is not just the atmosphere. It's not just the ocean. It has carbon. And here what you see are the first simulations that we did on Alps not that long ago. For the very first time, we took a full Earth system model at a kilometer scale using the new Grace Hopper 200s, and we're able to simulate how the carbon cycle evolves. So it's not as exciting, you don't see the motion of the clouds, but what you're seeing is the daily cycle, and for the very first time at this scale, you're seeing the flow of carbon through the system. So if you look over the Amazon here, what you'll see in green is the drawdown of carbon during the day, and in red, the respiration of carbon during the night. It respires during the day as well, but it's overwhelmed by the drawdown, and at night you just see the respiration. And you see things that, again, nobody has ever seen before. These simulations are just finished. You see the imprint of storms on the uptake of carbon. So these little speckling are the downdrafts from storms and the cold pools that fall out. So you see this interaction between how carbon flows through the system, how energy flows through the system, how water flows through the system. So a full representation of the entire Earth system at scales people care about is now possible, and you see that in these simulations. You also see it's coupled to the ocean, and you notice by now maybe that the ocean tends to be green, drawing down carbon in the extratropical seas around the Antarctica. And in the tropical seas, you see an outgassing of carbon. So not respiration, but the ocean is giving the carbon back. So we can see, you see a ship actually goes across there in that simulation. So there's not a real ship, but the data of the ship was shown in the middle before. You could see a slice right there in the green going around. So you see this full interaction. You look across to Africa, and you see the river valleys. Again, the imprint of storms. So now, especially on the Grace Hopper, we're able to deal with this manifold complexity of carbon cycle, of ocean, of land, of atmosphere, of vegetation, to look at the world in new ways. We have the hops that we need. So let me go a little bit into what's involved there and how the computing works, or what's the landscape of computing, and can we really make enough beer to serve the world, so to speak. The landscape of climate computing is shown here, and tau is just the compression. So tau shows you how many days you could simulate in a day. So 10,000 means that you can simulate 10,000 days in a day, or maybe, 30 years or something like that in a day. The x-axis is the scale of the atmospheric circulation. The ones we want to do are here at 1 kilometer. The red squares are scaling computations we did on our CPU machine called Levanta, and what we do is we run the model coupled atmosphere-ocean, and in this case we're running at 80 kilometers. That's what most people consider a high-resolution climate model. And we use more and more computational resources until we don't get any good returns. So we hit this strong scaling limit. So as we kind of go up, we hit the strong scaling limit, and I drew where that was in these calculations. That was that square. You know, we can get more throughput, but we're not using the resource well. And so this is an 80-kilometer model with a 20-kilometer ocean, and we get close to 30 years a day on 64 of these Milan nodes on Levanta. The dashed line shows the weak scaling of the strong scaling limit. So if I refine the grid, planet's the same size, I make the grid finer, so I have 4 times as many grid points because I refine it by a factor of 2. I have to take twice as many time steps. I can use weak scaling to make to solve the problem, but the throughput goes down because I need to take more time steps. And because of that, the dashed curve goes down. So that's what we can compute these days with this sort of model on a CPU-based machine. You can then put the machine there, and the machine on the bottom left of the curve, it shows what's computable. Anything to the upper right of the curve is not computable because you just need more resources than you have. And what you see in those calculations is that there's enough machine left. I could get more throughput by just running multiple copies, ensemble members. I can run it many times. As I move down the weak scaling line and I meet the machine line, it tells you I need the whole machine to run one simulation. So this is kind of where most people operate. We want to operate here. So on Lumi, we've been doing the same thing, but we've ported mostly through an OpenACC port. Lately, we've been using some of the DACE technology from Torsten's group. We're looking here. This doesn't use that in this case, but some of the other stuff I will show is. And this shows the scaling on Lumi, and here we're going from 10 to 5 to 2.5 to 1 kilometers. And again, we show the weak scaling of the strong scaling limit. And you see we can scale out to the full of Lumi, and we're getting at about 1 kilometer, we're getting about 100 days a day, something like 70 or 80 days a day. The difference between the red and the blue is that the red and the gray has the atmosphere and the ocean at the same scale, whereas the red, normally the atmosphere is so coarsely resolved, people run the ocean at a finer scale. But the cool thing on the Grace Hopper was we were able to use the complexity and the heterogeneity of that architecture to match it onto the complexity and the heterogeneity of the climate system for the first time. So it actually became an advantage of having this wickedly performant Grace CPU and then the Hopper GPUs. And that allowed us to go from the atmosphere of the ocean to simulate the Earth system for the first time. So these are the Grace Hopper results. And that run on the right, the R2B1111, was the 1 kilometer run with the full Earth system that we did on Alps, and which we're running now on Jupiter. We got on it yesterday, I think, for the first time. And we'll be running one of those simulations for the full year. So really, the hops are there. We can do this. And you can see on these blue lines, we still, we're running 1 kilometer at about 100 days per day, and there's still about 3 times more machine left. We have 2,000 nodes. It's about 6,000 nodes on Jupiter. So we can do a lot more. The machines have gotten to a point where we can just represent the full climate system with unprecedented detail. So I call this here, this is hopped beer, and the other stuff is Greit, and we have the ability to benefit from hopped beer. And these are the things that got us there. I like showing this picture because that's Jupiter. And normally if you go to Fugaku, they draw back the curtains. It's a wonderful stage. It's brilliant to watch it. Or if, Lumi and Alps are like that too. They have these great pictures. But Thomas Lippert, I don't know if he's here. He has he has more of an industrial touch. So he says, let's just put these things in containers, and you have pumps and things buzz and hum. It just has grit. So I actually really, really kind of like that. The only thing that's missing is graffiti. I think if we had graffiti, it would be even better. Okay, but what's coming next? It's not stopping there. It just seems we go from Grace Hopper. We're going to have Blackwell, and already people are thinking about Vera Rubin, and so we can say, what could we imagine still to do? And I think there's something we could do, and this is a challenge to that guy who's a bit fuzzy, Jensen, is to let's see if by 2030, I wanted to put down a challenge to the NVIDIA team, is if we can get to this scale. So the grand challenge, this is 100 meters. And I think we can, if we want to. We can get to 100 meters and simulate a trinity of 42-day simulations. And if we could do that, we could look at 2 really important questions of the climate system, which is how clouds will respond to warming, and how the aerosol, the particulate matter, affects the behavior of clouds and the forcing of the climate system. And these are the key things we need to know to get the hitchhiker's answer, the sensitivity of the climate system to forcing, is how the clouds respond and how the aerosol affects the system. And at that scale, we can do it, and we don't need long simulations for that if we're clever. And so here's a challenge by the end of the decade is to put to rest this question of Earth's climate sensitivity. Sorry, Jensen, for that picture. It didn't turn out so good. But good, we get the 42, we get the answer to climate sensitivity. And if any of you saw this talk I gave at SC in 2020, I had this little cartoon which should play.
All this trouble to make a big machine to make an ultimate answer to an ultimate question that doesn't matter anymore. But the beauty is doing that allows us to do what we need to do next, which is to create information systems that we can go into, and we can literally grab the Earth, anyone.
2 weeks ago, when I visited Thomas Lippert, I stopped by ECMWF with Destination Earth, and there I was. I could grab the world. They were using Apple's augmented reality. They took the simulations we made at a kilometer, and they threw it in the reality, and the guy let me play with it. Andreas Müller is doing, that's the guy, he's the genius behind that. This is the potential vorticity. I just switched it to look at the clouds. And I don't know if you've done this before, but it's just fantastic. You just take these things, you see the room like it is, and the globe is right there. You just hold it in your hands. I was trying to pet it and turn it and whiz it, but you could go into that, and you could really do what I was imagining only 5 years ago. I could do this here in a few minutes in his office of looking at that. Here I was trying to turn it, but I wasn't close enough. But you see, in my eyes, I'm holding that globe in my hands just like that. That's what I'm seeing. And I'm turning it, and I'm saying, there's a tropical cyclone somewhere. Can I see that? Oh, where is it? And then I look, and here I said, let's go to another model and look at it. So I click, and I get to another model that changed. So once I was looking at the one model, and then I switched to another model. So it's multimodal. It's got many channels. There's the cyclone. It's hitting towards the east coast of the United States to ruin the parade on Saturday, and it's going to go up the shore. And then I look at the clouds over Peru. And then I have a friend in Australia, so I turned the Earth and I went and I looked at Australia. But the point is the barrels, you can sort of maybe see them. But I had an important phrase there before. I said, you can do that. Anyone can reach in and grab the world. But of course, not everyone can go to Andreas Muller's office at ECMWF and go do that. This also doesn't really scale yet. But there's another guy in that same building, and it's that guy, Christian Lessig. And what I found fascinating about him is there's just reams of people working on AI. And I think most of them are working on the wrong problem. But he's working on the right problem. And in his paper on Atmosrep from a team in Jülich, now he's at Destination Earth, he said, let's solve this problem, which he says, let's look at the climate system P tilde as a probability distribution of possible states of some variable y tilde, and it will depend on some input state, x tilde, and some condition, alpha tilde. And alpha tilde would be things like the day of year, the CO2 concentration, whatever you want. X tilde might be the SSTs associated with sea surface temperatures associated with that. Y tilde might be the storminess or something that would come in a Köppen diagram. And he said, that's what we want to model. We don't want to replicate a climate model. We just want an AI representation of the data that we produce with physical simulations. So rather than trying to replace the climate model, what you want to do is have an AI representation of states that are consistent with the climate model. This is what he was thinking about in terms of Atmosrep, and he did it more for the weather picture. And the people who took this picture and brought it full circle to climate was a group led by this guy, Noah Brenovitz, who's working with NVIDIA, and a team led by Karthik Kashinath. And so here what you see is they took this approach and they used diffusion-based modeling. And they trained it on our models, so simulations are up there on the upper left. They trained this way of generating diffusive-based, coarse-grained representations of the climate system, given a field of sea surface temperatures. And from that, they can create a coarse-grained view. And so here, I have that here. That's the training data. They train models. You give this is X, the input. You give it a condition here, the 2038, the 25th of October at this time. And then you say, what's a possible state that could emerge, given the statistics of the climate model that you learned from AI? What could that look like? And they use generative diffusion to generate coarse-grained representations of that, as many as you like. And here's the coarse-grained version on the upper diagonal, and the fine-grained, then they use this multipath diffusion to fine-grain the 100-kilometer thing to 5-kilometer. And they do this with multiple channels, so you just have one sea surface temperature field. You generate coarse-grained resolutions, you go to super resolution, and you can switch channels. That's what's done here. The other thing, the beauty of this is, though, that you don't just generate a representation of the data that you simulated. Because it's got this alpha, the conditioning, you can say, well, what would it have looked like if there happened to have been a tropical cyclone over New York or the East Coast on that day? Can you generate that? And then here, what you see, this picture up here is different than this picture here. There's a tropical cyclone here. So you can do this with the diffusion-based modeling. You can try to create scenes that are consistent with the data. And this, in my mind, is a really big step forward, and it's a really big deal. They brand it as climate in a bottle. And it's a really big deal because it doesn't pretend that it's simulating the climate system. What it says is, let's assume us climate scientists know what we're doing. Let's assume that the data that we collect since the days of Köppen is somehow right. Let's try to figure out if we can use the AI. These are let's call these real cats. And then you ask the AI if it can draw a cat that looks like your stable of cats, which is consistent with what it's seen before. So you make reference to the training data in a very explicit way. You tether to the training data. And that's important because the training data can be certified as a public good. If you're giving out climate information, say if you're in the business of giving out climate information, you're selling it, what if you screw up? What if somebody builds a dam based on your information, and the dam breaks, and 20,000 people die? Somehow you need to show that what you did was based on the best available data, and you did the right thing. And so certification, these rules are really an important part of this. So the beauty about climate in a bottle is it's the barrel. It allows us to transport the information in a super reduced way, But it does it in a way that also allows you to build a legal framework or a framework of rules which say that you're doing things in the best possible way, that you're representing the training data faithfully, that could be tested and certified. So that's one really big deal. The other is that because it's this sort of, in my GTC talk in 2022, I introduced the idea of tethering. So the idea was just to use AI compression. But at the time, I was thinking of just really representing what we simulated exactly, rather than representing something that's consistent with the statistics of the system, which if you just think of that lesser quantity, this fuzzy thing, fuzzy tethering, is that allows you then to generate many scenarios. As long as you stay somehow consistent with the statistics, you can generate many scenarios from the same training data. So you can explore scenarios, you can explore variability, and you can ask questions like, can you create a scenario, maybe we're mad at Fugaku and we want to say, what's the maximum amount of rain we can create in 48 hours over Kobe? How many different ways can you give us this? So these are things that you can do with these methods, but you're not pretending that you don't know anything. In fact, what you're doing, and that's great if you want to market the information, is you're putting the blame for the quality of the information on the scientific enterprise, and all you have to show is that you're doing the best that's possible. So to me, this idea of fuzzy tethering and climate and bottle is a huge step forward. You put the climate in the bottle, and you end up with a climate information system which looks like that. So as opposed to the first one, where over here you have the world of data. This could be C3S, Copernicus Climate Services. It's collecting all the data, everything we know about the world based on measurements. Here you have projects like the DG Connect's Destination Earth project, where you're simulating different future scenarios based on the models that I showed in part one. Here you might have the academic community playing with their toil models or regional downscaling. You just take all of that information in the same way that Köppen did, but instead of having Köppen here trying through his wise head and long beard to figure out what it does, is you have a public-private partnership here creating these generative models to give you faithful representations of this information. And this is like a mega compression. What it does is it takes an exabyte of data and turns it into a terabyte of data. And that you can handle pretty easily on the laptop. And that allows you to scale across all sorts of sectors to fine-tune and refine that data so it actually responds to what people really want when they're thinking about public services, finance, water security, environment, agriculture, and on and on and on and on. And to me, this is the basis of a Klimahansa, a way to move forward in an uncertain world and share climate information. This could scale. And that brings me more or less to the end, is today I can hold the beer in my hands. These are the high-resolution simulations. And I can share it with a few friends, which I will quick do, because one of the friends is over here, and her name is Claudia Frauen. She made a lot of these simulations possible. Where is she? There she is, right there. Yeah. And I have one more. I'd give it to Torsten, but he doesn't drink. So you can have one as well, so I will give one to Torsten. And you can give it to another friend. So today I can hold this beer in my hand and share it with a few friends. But with the right rules, we have the way to transport the beer, but with the right rules and alliances, like we did with the Klimahansa, we could also share this with everyone. And so with that, I would just like to thank some of the people who made the talk possible. Apologize for going a bit over, but I hope you had a bit of fun. And thanks very much.
Thank you, Bjorn, for the amazing keynote. So let's take a few questions. It's kind of hard to see hands.
And if you
from up here.
have a question, we're asked that you use the mic because
Yes,
it's
please
recorded.
come up to the mic. There's one there, and one over there. Yes, I think I see someone going to the mic. Yes. All right, Nicholas.
I ask questions for a living. I live in the South Pacific. Climate, it's important to us. I mean, there are islands who are literally disappearing. Certification for the data that you are presented there. How is something that will be homogeneous in order that data from the South Pacific could enter into destination Earth and we can build that dam or whatever? I mean, how can we have a homogeneous amount of information to take the same amount of decisions north-south?
Yeah, this is what I like about being able, so when we compute globally like this, we had this project many of us were involved in called EVE, Earth Virtualization Engines, and the phrase we came up with there was this idea of local granularity globally. And so what you find out now, like if you live in Switzerland, you have great information locally. They do this downscaling, super refined information. Everyone in the climate community, my colleagues academically, they like to kind of lament the situation of the small islands, but they run climate models where these small islands don't even exist in the models. And so here, when we're at a kilometer or 100 meters, that data exists globally. So a few weeks ago, we had a global hackathon. And we found out one of the things is that with just a few global centers, we could open that data, especially using kind of cloud-ready data methods. So we use cataloging and ZAR. We use a hierarchical grid on HeelPix. It allows people to zoom in. So we had people from 5 continents. We had 10 sites, 700 people, all accessing the same data in the same formats and using it. So that's one way, and that we're showing works. But the other thing is this climate in a bottle. You know, hopefully they don't throw the bottle in the sea and you have to wait for 300 years until it arrives on your shore and then you can unwrap the climate. But the idea of super compression, so if we have that basic data there, and then if you can do this mega compression of the data, it allows you to go very, very quickly, if you have a million-fold reduction in the data, explore lots of scenarios, and because it's really connected to the simulation data that it was trained on, if you find something that is troubling or is really worth it, then you can go back to the data. So that's why, to me, it's really critical not to try to, you know, this whole business of trying to compete with the simulations. The question is, what does physics do well and what does AI do well, and find this harmony. And I think part of what AI does is to transport. It's the barrel. It can transport the information that we can create at a few centers around the world that has homogeneity in scale, and it becomes suddenly available to everyone. And so this is what we're seeing when we expand the problem in this way. And this hackathon was just fantastic. You just felt like everyone was in the data. So for this, I think, has to work if we want the data to be distributed. If we go with Krippen's way, you're just out of luck. Yeah.
When do you think you'll be able to generate statistically sound probability distributions, posterior probability distributions for making decisions, like we usually do? We generate 1,000. They obey detailed balance, so we know there's some good statistics behind it. And then you would play the usual statistical game, sampling from the posterior, saying with a probability of 20%, or here's a P50 that rises the sea level so and so much at this location. I think you're still a little bit away from that. Is that right?
Yeah, I could answer that. There's 2 answers to that question. One is never, and the other is now. And the way I think about that is, if we frame this as a question of quantifying confidence, how do you do that? We're talking about the future. The future isn't here. And I think we just fool ourselves. So we spend endless amounts of time being over-precise in quantification of uncertainty. What we have to do is give people physically consistent ways to sort of imagine the future. So when I think if someone's reaching into the computer and grabbing the world or playing with the data, we have to say, what's our best shot at giving them a way, like they viewed this blue marble, of viewing what the world could look like. If we try to communicate the fact that we're going to give you the sort of precision that you can do your tolerances within 10% margins or something like that, I think we're all just fooling ourselves. But what we lack as humans is a way to imagine, that Latin glacier. I don't think certainly they couldn't imagine that when they built the village over hundreds of years. So we're making decisions today where we have a hard time imagining what could happen. And we don't want to just open up this to fantasy. We would like to do something that's physically grounded, that's physically consistent. And I think we need to put that in people's hands and let them explore. And then they'll make decisions, and some of it will be based, the model will distort things. So that's the never part. And so the now part is, I think it's useful now, but if we try to pretend that we can be over-precise about the future, I think we're just fooling ourselves. But I would maintain there's value even if we don't, aren't able to quantify the distributions to, within the, certain margins.
Hello. That would be a question on the Board of Science and Sociology Politics. We all here appreciate the beauty and depth and the predictive power of those models, but the most uncontrollable force on Earth systems are humans, and the climate affects things like famine, food shortage, and influences migrations. Some of the biggest political issue currently are migrations of people, immigrants. How can you promote and inform political forces on incoming shortages and possible human movement?
So this is, I tend not to pay, I'm not a big fan of politicians. Some are great. We work with some in the city, actually, who are really terrific. It's not that they're bad or good. It's just that politicians, in the end, their job is to get elected. And where I think we can help politicians is by how we influence the people who elect them. And so, or who put them in power, if it's not elections. But in some ways, politicians kind of emerge out of a social consensus that these people should lead. So how do we influence how people think about the world? And if you look at what people like to call the Anthropocene, I have my own take on the Anthropocene. For me, the Anthropocene is global scaling and local governance. It's the contradiction that comes about from the fact that people know how to locally govern, but we have global influence. And that leads to this sort of unstable system where a few actors can accumulate wealth, where pollution can spread around the world, where we can have huge inequality, where we can have mass movements of people, so you can act. Individuals have this way of acting globally, but we don't know how to regulate that. We don't know how to make treaties with other countries to deal with issues like immigration. We don't know how to bound global finance. We don't know how to. We don't have a good grip on global governance. And I think if we want to govern something as a species, we also have to have an intuition for it. And so then the question is, what are the tools people need to develop this capability that we're gonna have to develop if we want to govern ourselves and our planet in the future? And that's why this blue marble picture is important for me, because it's a one small, humble attempt to show how, if you can change the way people think about the world, you might change how they influence the world and politicians. So you could think of this as the long-run approach to doing what I think has to happen, which is that we have to think about our world differently now that we can impact it globally. And here we're trying to make tools for the Anthropocene, tools that allow people to imagine different futures in ways which are based on the best possible science. And yeah, it sounds fanciful, but it's the thing that keeps me happy at night when I think of myself contributing to global well-being.
Oh, yes. Can you go to the mic?
So you talked a lot about the future. Now, imagine a situation where you take your model and try to simulate, or could you simulate the past? So you go back 200 years and take the CO2 concentration and other data available, run it through your model, and then basically show that the outcome fits the data available from that time. So it's a different approach, looking at the past to basically have a point of proof that the model will predict the future correctly.
I agree. I tried to do that. That was a little bit the idea of the blue marble. So that was 52 years ago. So it's not ancient past. It's not 200 years ago. But we had pretty good data at the time. And the idea was, in showing those two pictures, was that what I tried to take you through, I said, here's the one picture of how it looked like, and here's how we simulated it. So if you believe that's a good representation, then you should believe what it looked like on the backside. So that was the argument I was making, is that here's what it looks like, here's what we could simulate. You could compare that. You can't compare the backside. There's no picture of the backside. But based on that comparison, you yourself could evaluate whether you wanted to believe that backside image. And I think this is also my way, again, I think if we try to become over precise in the information and pretend like we really know what we're doing in great detail will be misleading. And I think much more informative would be in these tools for the Anthropocene, in this toolkit. And when you let people play with their future, they should also play with their past. So if you're in that valley in Blatten and you're wondering about what a rainfall event could look like or a permafrost recession could look like, you should be able to scroll into the past too and say, when I was a kid, there was way more snow. The powder was, we had Japanese powder. Does the model get that? And if it gets it, then maybe you're a bit more confident in it. And so I think this is really part of the game, is we need to allow people to have ways to assess the information. And that, again, means scale. So a lot of people say, high resolution, it's so expensive, you can't do this. But you have to do it because that's the scale on which people can assess these sorts of questions. They know what the world looks like on their scale, and they can say, that's just crap what you're giving me. That doesn't make any sense. The world doesn't look like that. I know what it looks like. Or, actually, that looks pretty good. So I think what you're saying is actually vital, but I would fold it in. You should be able to dial both ways.
Okay. So I think we have more questions, but we have come to the time.
People are thirsty.
So, yes. So let's thank Bjorn again for changing the way we think. And thank you all for staying until the end of all of today's program.